Okay, on this problem it says the cost C in dollars of removing P% of air pollutants and the stack emissions of a utility company that burns coal to generate electricity is given by this function. Cost is equal to 75,000 P over 100 minus P. Once you complete a table and so on, now this is a rational function. So we could do some of this on the rational sheet. It's not a messy one. It has a common denominator and so on. So let me go to the rational sheet. The coefficient for the linear coefficient on the top is 75,000. That's right there. And see, here's the format. C1, the linear coefficient is 75,000. There's no constant on the top. And down here on the denominator, so that could be 0 or deleted. Either way, it doesn't matter. On the denominator for that function, we have 100 minus p. So the linear coefficient is minus 1 because we have minus 1p, and then the constant is 100. So let's put those in. Minus, let's delete that out. Linear coefficient is minus 1 because minus 1p, and then a 100 right here. Let's look at this graph from, I don't know, 0 out to, let's say, 90. So that's from 0% pollutants cleaned up to 90% of pollutants. We can get do that table here. You know, what's the cost to do 0% pollutants or 10% of pollutants? There, 8,300. Or you can do a whole table here, 0 incremented by 10, and there's your table made up. Look here at 100. You get this thing right here. Look right here. It says division by 0. Why? Because if you put 100 into this expression, you get 100 minus 100 in the denominator. So that would give you 75, I think 7,500,000 or so when you put a 100 in here, 100 times 75,000 over 100 minus 100. It gives you a non-zero number over 0. Well, if you use any calculator and you do division by 0, let me do that. So if I menu, run, let me do 5. Okay, divide by 0, I get error, but I get error on that 0. So that tells me there's either an undefined point or a vertical asymptote. And as long as it doesn't make the top 0, then there's a vertical asymptote. Because after all, on that good page of notes that you should pay attention to, this one right here, how do you find vertical asymptotes? You set the denominator equals 0. So when I see that the denominator equals 0, that's a good indication that there's a vertical asymptote. Now, if it also makes the top equal to 0, then there'd be an undefined point there, and that comes up in section 2.5. So anyway, I can complete the table, and it's all getting to the question about the vertical asymptote. You can put in values that get closer and closer to 100, and you can see that it gets larger and larger. You can see it on the graph here too. Like here, put in 90. Look at the cost, 675,000. How about 95? It's 1,425,000. How about 99% of the pollutants cleaned up? It's $7 million. You can even do 99.9 and get $74 million to clean it up. But 100% just can't do it. Get division by 0. Now graphically, what does that mean? Well, look at this graph clear out to 99. What's it doing? It's going vertical here. There's a vertical asymptote that the graph gets closer and closer to. Where is it? 100. What's it heading off to? Infinity. Okay, so the big question on this was, does the graph have a vertical asymptote? Yes. If so, where is it? It's 100. What does it tell us about the cost? It means this. As the percentage of pollutants approach 100, the cost is approaching infinity. Okay? You can write it this way. The limit as the percentage of pollutants approach 100. Now the negative right there. Okay, so let me make this as big as possible so you can see it here. Right here, this negative means looking to the left-hand side of the graph. That's what that negative means. As the percentage of pollutants approach 100 from the left, what is this function, the height of this graph getting close to? Well, it's approaching infinity. Infinity is the right answer. Sometimes you may even have to type that in on a test, infinity. So look, on the left-hand side, here's 100. Looking on the left-hand side, what's approaching? Infinity. And that would be the answer to the problem. It's as easy as that. Okay, so this is the stuff that I've mentioned before to pay attention to with vertical asymptotes, horizontal asymptotes, and so on. And let's go on to one more problem, this one here, the learning curve problem. So this is the number of trials that you get, like taking your driver's test over and over and over and over and over again, and this is the percentage correct you would get on your driving test. So first one here says determine the percentage, how many trials it would take for someone to get 84% correct. So this would be 0.84, and then you have to simplify this stuff on the top. Well, 0.7 times n is 0.7n. 0.7 times minus 1 is minus 0.7, plus the 0.5 is minus 0.2. Simplify the bottom, and you get this. So now solve this equation, and the way to do that is just cross multiply is all you do. So you take your 0.84 times this 0.8n plus 0.2 equals this, and then use a calculator to help you multiply this junk together. You just need to solve this equation. Take this through, and then take terms to the other side, and you get it. And you'll get 13.14 when you solve that. Okay. So now, what is the limit as n approaches infinity? In other words, if the person gets more and more trials, what percent correct should he get? You might think 100%, but that is maybe what you would think, but not all tests can you reach 100%. So on this, you're looking for, anytime the independent variable is approaching infinity, you're looking for a horizontal asymptote. How do you find a horizontal asymptote? Well, that's from right here on this, horizontal asymptotes. It's looking at the degrees of the numerator and denominator. So let's look at the degree of these things. So going back to it here. On this problem, here it is kind of simplified. What degree is the top? First degree. What's the degree of the bottom? First degree. When the degrees are the same, it's just the leading coefficients. So it's 0.7 over 0.8. So it's approaching 0.7 over 0.8, which is 0.875, or 87.5% correct. No matter how many trials you get, that's what it's leveling off to. Now we can graph this after you simplify to get down to this. So 0.7 minus 0.2, let's put those coefficients in. 0.7 and a minus 0.2. And on the denominator, it was a 0.8, I believe, and a positive 0.2. I think those are the right coefficients. And if we put it in larger and larger numbers, what's it approaching? Well, look, here's at 100. How about a million? I get 0.87499, so very close to 0.875. As your number of trials here gets larger and larger, your percentage correct levels off to this value right here. What is that? It's not 1. If you want to see it, we could maybe go out a ways. Let's look at the graph from 1,000 or 10,000 to a million. There you go. How about that? What is it? Look. It looks like there's a curve to it, but look, it's basically 0.875 the whole time. Or if I look at it, let's go from 100 out. Look, it's flat line right there, 0.875. That's the horizontal asymptote. Don't want to do it graphically. It's pretty rough that way. You can put in large numbers here if you can use Excel, or just use a calculator and put in large numbers. Or what I do is I just do the leading coefficient. Well, you do the degrees, and if the degree is the same, it's the coefficients. 0.7 over 0.8 is 0.875. Need to know this: if the degree is bigger on the bottom than the top, then it goes to 0. And if the degree on the top is bigger than the bottom, then there is no horizontal asymptote, and it goes off to infinity. So I think we can stop right there.